Hi, in this video, we want to take a look at hierarchical clustering. Hierarchical clustering is another way to go about clustering, but in this case, what we're doing is we are taking our entire data set and then we are breaking it down into two smaller groups. Then we break down one of those groups into two smaller groups. Then we take one of the three groups and we break it into two smaller groups. And we keep on breaking it down into smaller groups until each individual point is in its own individual cluster. Okay, the other way to go about hierarchical clustering is that every single point is in its own cluster. Then I combine two clusters together. And so now I have n-1 clusters. Then what do? I go and I find two clusters and I combine those. And then I find two clusters that are similar to each other and then I combine those. And we keep on doing this until we have one big cluster that includes all of the data. And that's hierarchical clustering. Something that's nice about this method is that first and foremost, we get kind of like a picture, a dendrogram, a tree, to show us what does our clustering look like. The other advantage to this is that if I want to have 2 or 3 or 4 or 5 different clusters, I get all of them for free. Yeah, I run the algorithm one time and I have all the various sizes of clustering that I want. Also, the clusterings are nested within each other. So if that's mathematically nice for our situation, that's something useful. That usually isn't important in statistics, but down the road, it might come up. One of the disadvantages of hierarchical clustering is that it takes a long time, specifically computing the distance matrix. That is the part that takes the longest. But once we have that matrix, we can explore a wide variety of clustering algorithms on that one matrix. So that kind of makes up for the lacking. All right, so why do we go through hierarchical clustering? Well, the first reason is to group observations into similar groups. Another one is that I can use the grouping to create a categorical predictor variable. And also I can do outlier detection. So divisive algorithms are ones that we take the entire data set into one big group and then we break it apart. Then we break the parts into smaller parts and smaller parts and smaller until we have individual points in their own clusters. So we start with one big cluster and break it down into n small clusters. Agglomerative methods, what they do, they start with all of the observations being in their own individual cluster, and then they start combining clusters until we get one big cluster. Both have their advantages and disadvantages. Honestly, my opinion, I don't really care how I get about my clustering. I just want to know how useful is the clustering to me. How I got there really doesn't matter to me. All right, so let's go ahead and let's look at an example. So once again, we're going to take a look at the decathlon data set. I like this data set because it's relatively easy to understand what's measuring, and it gives you some interesting results when you do the clustering algorithms on it. So just like I did before in the other videos, I take the data and I reduce it down to the measurements I'm interested in, and then I rescale the data. When I do clustering, I want to rescale my data, or the column with the greatest variance is going to dominate the results. All right, so now let's talk about a distance matrix. A distance matrix is going to be a table of numbers that measures the similarity between every pair of data observations. So if I have 100 observations, this is going to be a 100 by 100 matrix. It will be a 100 by 100 table of numbers. All right, well, just to kind of give you a feel for what that looks like is, so here we take just 5 different athletes and we compute it. Now, in computer science, there's a standard way to store this. So if I take the distance from, let's say, think about this, the distance from A to B and the distance from B to A are the same. So if I actually have a 100 by 100 table of numbers, almost half of my values are going to be redundant. So what R does, it stores it in this kind of triangle format. And if you look here, if we count the names 1, 2, 3, 4, well, Clay's already been picked up. Karpov's already been picked up here. Bernard's been picked up here. And here's a new one. So here I've got 4 names, I've got 4 names, but these are 5 different athletes. This is a way to kind of represent the table of numbers without using as much memory space on your computer, which is good, And if I look at it, I can see that it looks like Bernard and Sabriel are the 2 that have the most similar outcome on the decathlon data set. And if I look here, we can see that Yurkov and Clay are the least similar to each other. And everybody, all the other pairs are kind of in between. Now, when I do this for hierarchical clustering on a full data set, it's going to take all the data points and make it a much bigger table of numbers. Initially, I had it in the document what the full decathlon's distance matrix looked like, but it was so big, I just got rid of it. It was just vomiting numbers onto the page. Okay, so let's go ahead and let's try to visualize our distance matrix. Okay, so if I look here, so what do? I take the distance function and I run it on my rescaled values. I call that dist_m. And what I'm going to do, I want to visualize this. Now, R has a bunch of ways to visualize different types of data. The heat map function doesn't want a distance matrix. It wants a regular run-of-the-mill matrix. So I convert it using @matrix with this function. And so when I do as matrix on the distance output, then this is a regular 41 by 41 matrix. And now what I'm going to do, I'm going to go ahead and use a Viridis color palette. This is a good color palette for data science. And here's the output. All right, what I want to see is I want to look and see, do I have triangles on the heat map plot? I'm looking for triangles. So you can see a kind of a triangle here. So intuitively, I can see that the bottom 3 athletes are relatively similar to each other. And we can see by this kind of tree-looking diagram, this dendrogram, that they group together. Now let's go over here. I see a rectangle. And if I look over here, I can see that these athletes are kind of getting grouped together. And there's kind of a triangle here, a little bit light in this region on the corners of the rectangle, but let's go ahead and accept it as being a group. Now, I kind of see a rectangle here, and then it's kind of hard to pull out what would be a group over here. It's less distinct. So when I see the darker values, that's an indication that 2 points belong in the same cluster. Now, the darkest values are the distance from an observation to itself, which will always be 0. So the smaller the distance, the darker the value. Now, I use the Viridis color palette. Viridis, what this does, this makes sure that darkness, hue, and intensity are all on the same scale. Think about the rainbow colors, Roy G. Biv. If you think about intensity, yellow is in the middle, right? Yellow is in the middle, so people will mistakenly see yellow on the rainbow color palette and think that yellow is an extreme value when it's in the middle. So because of that, we want to avoid using the rainbow colors if we can. There are times where it's appropriate, like I have discrete values, only have a few values that's good, but the more values I have, the less I really want to use rainbow because people tend to interpret it incorrectly. Here, if you look at these values, the color along the rainbow, the hue, and the intensity all go along in the same direction. So that makes it easier for people to interpret what's going on. And this is a good color palette for those who are colorblind. Now, another way to visualize this, and this is really the same visualization, just looks different, is using the, what is it, Facto Extra package, FVisDist, so a visualization of distance. Now here it orders everything differently. It doesn't give us a tree diagram, but we can see pretty clearly that these guys look like they're in a group of their own. Looks like Clay and Sabriel are a group. and these athletes might form a group, these three, and maybe up here. Now, the QGraph package enables us to represent the distance between the observations in like a network graph, where the input is 1 over the distance. So the larger the distance, the more far away they are from each other. Divide by a big number, I get something small. So if 2 points are far away from each other, this will be very, very small. And here's what the picture looks like. And so the darker, thicker lines indicate that the athletes are more similar to each other in their data. All right, so now let's do actual hierarchical clustering. So I just take my distance matrix, I drop it into hierarchical clustering, and I plot it. All right, now here is what the dendrogram looks like. And what we've got going on, let's say that I want 2 clusters. I'm going to go here, I slice along here, and you'll notice I'm cutting once, cutting twice. All the points that connect to this stem are in one group. All the points that connect to this stem are in a different group. Now, if I want 3 clusters, I go through and I cut along here. So 1 cut, 2 cut, 3 cut. So this cluster stays the same, but over here, these 4 values are now in their own cluster, and all of these are separate from those 4 values. If I go a little bit lower, we can break it up into 4. Let's see, this was 3, 4. We can go 1, 2, 3, 4, something like this. It's easier if you have like a piece of paper to cut, or you let the computer do the cutting for you. And I can keep on going down and lower and break it up. Now, when I plot this, I have the option of making these stems going all the way down, so it's a little bit easier to do this cutting. I like to have it broken up this way because it emphasizes where the splits are. It's up to you what works best. All right, so I was looking at it, and I'm like, I'm going to go with 4. So if I remember correctly, the Caesarea will be by itself, then these athletes, and then all of these athletes will be in one cluster. To get the clusters from a hierarchical clustering, I have to use the QTree function. I think it's supposed to be cut tree because you're cutting the dendrogram, but it's spelled QTree. It's cute. It's cute. All right, so now I want to go ahead and plot and see what's going on now that I have a clustering going on. And I use ggplot for this, just like I did with the k-means video. All right, so here's my clustering. All right, so I've got a couple of points in teal, some points in green, a bunch in red, and I notice that this point is off by itself. It's in its own cluster. All right, so this clustering is indicating that this point might be an outlier. I would want to double check. Maybe there's an error in the data. Maybe there's something special about this athlete that I don't know about right off the bat. But I would want to inspect this particular athlete further before I would go out and start modeling. So this is a good example of using hierarchical clustering for outlier detection. A silhouette plot makes a bar plot for each individual point. The farther the point is, the farther the bar is to the right, the more confident I am that that point is in the correct cluster. The farther that bar is to the left, the less confident I am. So whenever I see bars pointed to the left, I want to take a look and go, hey, are these points in the cluster that they belong in? Now, every time I've done this professionally, I've always had a few bars pointed to the left. That doesn't mean they're in the wrong cluster, because if I move around points, that's going to throw off the clustering on other clusters with other points. So I might have optimal, I might not. I want to just kind of look at it and see, does it look good? Does it look reasonable? So let's take a look at this. All right, so here's the silhouette plot. Remember, the first cluster had the most points. And so that's here. Then the second cluster, then the third, and then the fourth. Now, the fourth only had 1 point. Because it had only 1 point, its right spot at the average of its point. So I don't see a bar here. Now, when I look here, I can see that I've got a few going to the left. There's only one that really bothers me on this one. So I would go in and I would want to figure out which point is this and go, hey, does this belong in a different cluster? Now, when it comes to the distance matrix, I have to choose a metric. I have to choose a way to measure the dissimilarity between our different observations. All right, so when I do hierarchical clustering, I need to choose two things. There are two parameters. Way I measure distance and the way I choose how the points get combined together or separated. All right, so first one is going to be the distance metric. When I do this, this is going to be the part that takes the longest to compute. So if I don't have time to explore a lot of different clusterings, I'm going to pick one time, I'm going to run it, and that's it. And then I'll go ahead and explore the different clustering algorithms on their own. All right, so how do I pick which metric to use? If I'm going to be using mean squared error or sum of squares error to evaluate the model, I'm going to probably use the Euclidean metric. That's very natural because that is the square root of sum of squares. Also, the Euclidean metric is usually the default method if I don't specify which one I want to use, and it's usually the fastest. If I'm going to use mean absolute error to evaluate a model, the Manhattan metric is a natural choice because that uses the one norm. If I have the time to explore different models, different metrics, I will. But if I only have time for one thing to do, I'm going to pick one distance metric to use and just run it. All right, so in R has a collection of different ways to go about this. And I sorted these by the order of what we'll see later in the video. But Canberra, Manhattan, Euclidean, maximum, and Minkowski usually give out decent results. The binary one, that's always 0 or 1. I've never had success with it, so I'm just skipping it here. Now here I'm using the lapply function to compute all of these very quickly and make a list. Remember, if I want to do things fast in R, I don't use a for loop. I use an sapply or lapply or a parallel apply function. Now, when I talk about ways to do hierarchical clustering, I have a bunch of different choices also. WAR-D works to minimize the standard deviation. WAR-D squared works to minimize variance. Complete linkage does a good job of making sure that everything in a cluster is similar to each other. We have McQuiddie, we have average, and we have single. Also, median and centroid are options, but I've never had success with them, so I just went ahead and skipped them. So overall, WAR-D does a good job of creating clusters of equal size, roughly speaking, and single does a good job of doing outlier detection. And it's kind of like along the spectrum, it kind of shows, are they better at evening out or are they better at finding the weird cases? All right, so after I choose my clustering method, so after I get my distance metric, and then I compute that, and I have to choose my hierarchical clustering method. If I don't have time to run through a bunch, I'm only going to do WAR-D or single linkage, depending on my problem. I might do both. But if I have the luxury of time, I will compute through all of them if I can. The step of hierarchical clustering is pretty fast once I have the distance matrix. So once I get that going, I can run through all of them. It's not a big deal. All right, so how do I select a clustering? Well, here, all this code just goes through and basically just plots different clustering. This step here is just basically getting rid of the margins so that I can, I'm not wasting any space. This is just going through and iterating over the different distance matrices and different methods of clustering. And then here, this is just plotting. and I'm not putting any labels, I'm not putting any axes just because I want to kind of look and see what's going on. And I'm trying to save space because I've got a bunch of them. And here's all of them, and there's a whole bunch. So looking here, we can kind of see that this Ward D with Canberra, these are kind of even looking, two even groups. And these look like these are pretty good for equal size clustering if that's important to me. If I look over here, I see like this Minkowski with single. I can see there's 2 points kind of just like hanging out by themselves. I might be interested in these as being outliers, whichever points are there. As I look here, this Manhattan single linkage, this 1 point is probably an outlier. I would want to like dig in, start looking. It's probably the same outlier here. Now, there's one problem with this is that if you actually start digging in, all these heights are different, and it's hard to tell which ones are actually the same. It's possible to get the same dendrogram, but with different heights. But the splits or the clustering are effectively the same when I say the number of clusters that I want. So what I like to do, I like to convert the height to the rank of heights. That way it converts everything to integers. It sets it up so that I have like the same scale for different dendrograms, and it makes it easier to read where the splits are. It's less crowded. So I'm running through the same code. I'm doing, I'm taking my dendrograms, I'm converting the height to the rank, and then getting rid of margins. And then I'm just plotting each of the modified dendrograms. So here, you'll notice that the height of the splits are more even as if you start like digging into each of the dendrograms, but these will actually give you the same clusterings when I declare the number of clusters that I want using Qtree. All right, so now how do I pick these? Which one is going to be the best? All right, I made the observation that in the cluster package, the coefficient of hierarchical clustering does a good job of telling me, is this better for outlier detection or is this better for equal size groups? All right, so if this is bigger, it's probably going to be a good one for equal size group. If this is smaller, it's probably better at outlier detection. So let's go ahead, let's run through all of these and compute this value and see what we get. Here I create a matrix to store the output, and the rows correspond to the distance metric. The columns correspond to the clustering algorithm. And then I just run through and I compute it, and I enter it into the appropriate position on the matrix. I went ahead and took a look at the matrix, and I saw that the Canberra metric with Ward D is the one that gives me the largest value. So let's take a look at that plot. So these are looking pretty even. You can see, first and foremost, if I say 2 groups, they're about equal size. Now let's go ahead and look at the maximum metric with single linkage. This one gave me the smallest coefficient. And we can see that Clay, cores is something or other, and Cass are all off in their own group. So I would want to take a look at these 3 as, hey, maybe these are outliers, maybe there's something wrong going on, maybe there's an error in the data, maybe that they belong there, I don't know. But this is an indication I need to take a second look there. Something that's important about this, if I want to compare the different ways or the different clusterings using this method, using this coefficient of hierarchical clustering, I need to convert everything to an equal scale on the height of the dendrograms, and that's why I did the rank. If you don't, if you're not going to run through a whole bunch of different models, don't bother with it. If you're, if you don't know what to do, just do Euclidean metric with Ward D and single linkage and call it a day. Be quick, be fast, don't worry about it. But if you want to dig in, start looking at your different options, then this is a good way to pick one. All right, that's all I've got. So hope you have a great day and take care.